Two giant swaths of radiation, known as the Van Allen belts, surrounding Earth were discovered in 1958. In 2012, observations from the Van Allen probes showed that a third belt can sometimes appear. The radiation is shown here in yellow, with green representing the spaces between the belts. Credit NASA Van Allen probes. Goddard Space Flight Center. Earth is surrounded by giant donut-shaped swaths of magnetically trapped, highly energetic charged particles. These radiation belts were discovered in 1958 by the United States' first satellite, Explorer 1. The discovery was led by James Van Allen at the University of Iowa, which eventually caused the belts to be named after him. Van Allen's experiment on Explorer 1, which launched January 31, 1958, had a simple cosmic ray experiment consisting of a Geiger counter device that detects radiation and a tape recorder. Follow-up experiments on 3 other missions in 1958, Explorer 3, Explorer 4 and Pioneer 3, established that there were 2 belts of radiation circling the Earth. This simple picture of the radiation belts persisted for decades until 2012, when a pair of probes was launched to study them in detail. This was the first time that 2 spacecraft simultaneously studied the radiation belts, trading information with each other to build a bigger picture. Part of the interest in the Van Allen belts comes from where they are located. It is known that the belts can swell when the sun becomes more active. Before the probes launched, scientists thought the inner belt was relatively stable, but when it did expand, its influence extended over the orbit of the International Space Station and several satellites. The outer belt fluctuated more often. The Van Allen probes, formerly known as the radiation belt storm probes, have several scientific goals, including discovering how the particles, ions and electrons, in the belts are accelerated and transported, how electrons are lost and how the belts change during geomagnetic storms. The mission was planned to last 2 years, but as of August 2016 the probes were still operating at double the expected mission lifetime. Usually scientists take a few months to calibrate their instruments, but a team with the relativistic electron-proton telescope asked that their instrument be turned on almost immediately 3 days after launch. Their reasoning was they wanted to compare observations before another mission, SAMPEX Solar, Anomalous, and Magnetospheric Particle Explorer, deorbited and entered Earth's atmosphere. It was a lucky decision, NASA said in February 2013, in noting that a solar storm had already caused the radiation belts to swell as soon as the instrument was turned on. Then something happened no one had ever seen before. The particles settled into a new configuration, showing an extra, third belt extending out into space, the agency added. Within mere days of launch, the Van Allen probes showed scientists something that would require rewriting textbooks. An artist's depiction of the 2 Van Allen probes orbiting Earth. Credit JHUAPL. Data gathered by the probes also showed that the radiation belts shield Earth from high-energy particles. The barrier for the ultra-fast electrons is a remarkable feature of the belts, study lead author Dan Baker, of the University of Colorado in Boulder, said in a statement. We're able to study it for the first time, because we never had such accurate measurements of these high-energy electrons before. Gallery. NASA's Van Allen probes. This new information helped scientists model the belt's changes. But there was more information to come. In January 2016, scientists revealed that the shape of the belts depends on what type of electron is being studied. This means the 2 belts are much more complex depending on what is being observed. They can be a single belt, 2 separate belts, or just an outer belt with no inner belt at all. The researchers found that the inner belt, the smaller belt in the classic picture of the belts, is much larger than the outer belt when observing electrons with low energies, while the outer belt is larger when observing electrons at higher energies, NASA wrote at the time. At the very highest energies, the inner belt structure is missing completely. So, depending on what one focuses on, the radiation belts can appear to have very different structures simultaneously. What is still poorly understood, however, is what happens when particles from the sun hit the belts during a geomagnetic storm. It is known that the number of electrons in the belts changes, either decreasing or increasing depending on the situation. Also, the belts eventually return to their normal shape after the storm passes. NASA said it isn't clear what kind of storm will cause a specific type of belt configuration. Also, the agency noted, any previous observations were done only with electrons at a few energy levels. More work needs to be done. Luckily, scientists got the chance to observe a storm up close in March 2015, when one of the Van Allen probes happened to be situated inside the right spot in Earth's magnetic field to see an interplanetary shock. NASA describes such shocks as similar to when a tsunami is triggered by an earthquake. In this case, a coronal mass ejection of charged particles from the sun creates a shock in specific areas of the belts. The spacecraft measured a sudden pulse of electrons energized to extreme speeds, nearly as fast as the speed of light, as the shock slammed the outer radiation belt, NASA wrote at the time. This population of electrons was short-lived, and their energy dissipated within minutes. But 5 days later, long after other processes from the storm had died down, the Van Allen probes detected an increased number of even higher energy electrons. Such an increase so much later is a testament to the unique energization processes following the storm. The shape of the Van Allen belts can vary widely depending on how energetic the individual electrons are, and general conditions in the Earth's magnetic environment. During geomagnetic storms all 3 regions in the belts can balloon. Credit NASA. GODDARDDUBERSTEIN. The Van Allen probes are specially radiation-hardened to withstand the intense environment of the belts. Some spacecraft, however, are more vulnerable, especially when a solar storm hits. At worst, spacecraft can short out due to an electrical overload. Communications can also be disrupted. Fortunately, sometimes instruments can be turned on or off on a spacecraft during a solar storm. Radiation, of course, also poses a human risk. Astronauts are subject to lifetime radiation limits from their time in space, to reduce any risk of cancer. Since only a few dozen people have spent 6 months or longer in space, however, it will take decades to understand the long-term effects of radiation on humans. The astronauts on the ISS do not regularly spend time inside the belts, but from time to time solar storms expand the belts to the orbit of the space station. In the 1960s, several Apollo crews went through the Van Allen belts on their way to and from the moon. Their time in that radiation-intensive region, however, was very short, in part because the trajectory was designed to pass through the thinnest known parts. With more study, astronauts can be better protected for long-term stays in Earth orbit. We study radiation belts because they pose a hazard to spacecraft and astronauts, said David Zubik, the Van Allen probe's mission scientist at NASA's Goddard Space Flight Center in Maryland, in an August 2016 NASA statement. If you knew how bad the radiation could get, you would build a better spacecraft to accommodate that. Additional resource: NASA Van Allen probes mission overview.